Efficiency analysis framework concentrates on the order of growth of an algorithm's basic operation count as the principal indicator of the algorithm's efficiency. To compare and rank such orders of growth, computer scientists use three notations. One is big O, another one is big omega, and other one is big theta. Informally, big O of g of n is the set of all functions with a lower or same order of growth as g of n. Thus, to give a few examples, the following assertions are all true. So, say an algorithm runs in big order of n cube, then I can say that n square is an element of order of n cube. Or I can say that n is an element of n cube. Or I can say that n cube is an element of order of n cube. Or I can say that 4n cube or n square is an element of order of n cube. So, those elements which are below n cube, including n cube. But it is wrong to say that n raised to 5 element of order of n cube, since n raised to 5 is bigger than n cube. So, this is not an element. This sign indicates element of a set. A function t of n is said to be in order of g of n, denoted by t of n element of order of g of n, if t of n is bounded above by some constant multiple of g of n for all large n. That is, if there exists some positive constant c and some non-negative integer n0 such that t of n is less than or equal to c times g of n. This is what I write here, like n square element of order of n cube, since or t of n should be less than or equal to c times g of n. For all, this denotes for all n greater than or equal to n0. For all n greater than or equal to n0. If, for example, a sorting algorithm used in the first part makes the number of comparison as n into n minus 1. N into n minus 1 means n square minus n. So, if you use big O notation, you need to take a highest degree polynomial, that is n square. So, you can write this one is big O of n square. And second part makes no more than n minus 1 comparison. So, in the second part you have n minus 1 comparison. So, the highest degree is 1. So, this will be big O of n. So, the efficiency of the entire algorithm is you need to take the maximum of these two, maximum of n square and n, that is maximum of n square and n is n square, that algorithm runs in big O of n square times. So, as a practical side, if you are given an algorithm and you need to find out the efficiency or time complexity of that algorithm, what you need to do is you need to look at the loop and find out how many times it runs or the basic number of times the basic operation runs. In the case of sorting algorithm, most sorting algorithm, it is usually n square, like selection sort, insertion sort. Then you can directly write it will be big O of n square. So if it is n, if the number of times it runs is n minus 1, then you need to write it as big O of n minus 1. Big O of n minus 1 equals, if you have something like this, then it equals the largest degree term. So that will be big O of n. So if it is big O of n square minus 3n, then largest degree term is n square. So again it will be big O of n square. So the algorithm runs in big O of 5n cube plus 3n. Again this will be big O of 5n cube, that is again big O of n cube. We need not worry about the constant term. So this is how you find out the time complexity or efficiency of an algorithm. Usually